Thank you, Adil. My name is Goran. I am working at the University of at UMKC at the supervision of Dr. Shaki Alman and Dr. Kevran. The title of my presentation today is Mitigating Steel Corrosion in Reinforcing Concrete Structure Using Hydrophobic Sealers. And the outline of my research is I start with introduction and showing the problem statement and all the way down to present some conclusions. So we know that concrete is not good in tension, while it's very good in compression. That's why we are using steels. So once we embed steel reinforcement in highly alkaline medium such as concrete, which has a pH more than 12 most of the time, steel reinforcement thermodynamically generate a protective layer, which is an iron oxide layer around the steel. And as long as the pH of concrete is high and the protective layer, or in other words, passive layer is over there, the concrete, the structure is in immune condition, and everybody happy because nothing is happening at that situation. But there was always, there's a problem. If we are looking at the American map, we can see in the northern state, for each storm event, we are using de-icing salt or an anti-icing salt. Not all of the salt contain chloride, but those contain chloride is more effective and economic, or in other words, is cheap. And on the other hand, in the East Coast and West Coast, and some southern states, we have the reinforced concrete structure, they have a direct contact with marine water, which is contain decent amount of the chloride. If we are looking at most of the corrosion model or deterioration model generated for predicting concrete surface life, we can see here that the concrete at the beginning is in immune system, but once the first time the salt application used or it comes in contact with marine water, at that time chloride ion was gradually diffused through the concrete cover. So it's the diffusion takes time and depend on the concrete cover and concrete depths, cover depths. We know if the concentration of the chloride ion at the concrete steel reinforcement reached the critical chloride threshold, at that time, the chloride depassivate the protective layer and expose the steel bars to corrosion. So once there's a water and oxygen, at that time the corrosion initiate. So probably most of you know that the corrosion product have as the expansive material has a volume to 2 to 6 times larger than original consumed material. So by time the corrosion product at the concrete steel reinforcement generate a tensile stress. As soon as the tensile stress of this productive material, corrosion material is higher than concrete stress, the corrosion crack will appear. So we can see here from the deterioration model as well, the initial immune system, diffusion condition, and chloride penetrate, and cracking is happening. Once cracking happening, because there is a direct source of oxygen and water, the corrosion will be accelerated very significantly. So in recent years, probably after 2000, so there's a lot of direction to improve the concrete surface life even more than the targeted age. So how we can preserve our concrete or improve the surface life of our concrete, we have to work at the condition where it's immune system. So one of the method or measure have been used for a while is surface treatment. Surface treatment can be classified into four categories: organic coating or continuous coating, pore blockers, pore liner, and cementitious layer. Cementitious layer is not scope of my research actually, and in this research we are focusing on the effect of penetrating sealer, which is the first three one is can be categorized for penetrated sealer. So experience and research show that for organic coating or continuous film is not good for the area that's especially for bridge decks or parking garage because of traffic loads. After a while, the continuous film will be peeled off and expose the structure as well. However, pore blocker is a type of material when you apply of the steel of the concrete surface, it's literally broke the pores, and at that time we can expect the reduced water and chloride ion ingress. The third one, we call it pore liner, which is the type of material once we apply to the concrete surface, generate a water repellent layer, which is don't allow water to intrude ingress to the concrete while it's still the pores is open for vapor transmission, which is very good for concrete structures because once for in the area that we have cycles of freezing and thawing. So I come to the objective of my research. So I want to use penetrated sealer as a very economic material and very easily to apply on the concrete reinforced concrete structure. And I want to see what's the effect of this material on the durability concerns, such as surface concrete abrasion and moisture isotherm and corrosion performance. So to do so, we designed our concrete mixtures and we casted our concrete, cured for them for 7 days and transformed it to the environmental chamber for 7 days as well and applied the sealer at the age of 14. After that, so the sealers we used in this research, all of them can have a mode of action of hydrophobicity, which is another word that water repellent and try to not water ingress into concrete. So the first one is we call it soy missile ester, and the second one we call it sodium titrate, and the third one is a 40% silane. We cannot mention that the product because of the US rules. So all of these sealers, first one it's a pore blocker, the second one is partial pore blocker, and the pore liner at the same time, and the third one is a pore liner. So based on the specificity of all of the material, we back calculated all of the sealers and we tried to apply 150 to 175 feet square per gallon. And after we applied the sealers, we return all material into environmental chamber and we tested all of the specimen after 28 days. Let's look at some results that we get from our experiments. So the first thing we looked for is the abrasion resistance of concrete. So after we casted our specimen and cured, and we looked for abrasion resistance according to methodology described by ASTM C944. The only difference, instead of what recommended ASTM is 2 minutes, but we look it for 2, 4, and 6 minutes at the same time. And after we tested them, the results show that very kind of like unexpected we got. So soy missile ester negatively affect the surface abrasion of the concrete. So after 6 minutes, the accumulation of mass loss almost twice much than untreated control. So we don't have a kind of like a concrete answer for this for why it's happening, but probably if we are looking at the chemical composition of the soy missile is a oil fatty, and which is we applied all of the sealer at age 14, probably stopped the hydration process, or that's why it negatively affected the concrete surface. While silane and sodium tartrate very effectively reduces the abrasion resistance of the concrete, and we can see from the visually that the concrete is more deteriorated here compared to the rest of the material. And probably you ask what the correlation between abrasion resistance of concrete and corrosion mitigation. Actually, the answer comes from we correlate this data, abrasion resistance, with the depth of the sealer penetration, because research have shown that each year 0.17 millimeter, all of the concrete pavement is wear. So within time, probably if we have a bad concrete at that time, the concrete surface will be wear, and at the same time we cannot trace the sealer material. The second thing we looked for is a moisture isotherm, which is we follow the procedure described by STM 1585 for 8 days. And we have been working with the evaporation rate using the sealer from the previous research. Actually, I presented in the last convention. So we think that evaporation must be considered because it's affected on the data. The evaporation rate is a similar procedure as a absorption rate. The only thing we flipped the sample and monitored them in the environmental chamber. If we are looking at the graph, we can see that all of the sealers reduced the absorption capacity, and but with a different range. So we can see soy methyl ester and silane significantly reduced the absorption capacity for 8 days, while sodium tartrate sealer was not that much effective. So after 8 days, we followed 4 cycles. We monitored our specimen for 4 cycles, 3 days drying and 4 day wetting again to kind of to represent what's going on in the real life. We can see here that specimen treated with silane and sodium soy methyl ester throughout the test method is steady. There's not much fluctuation, while control and specimen treated with the sodium tartrate is fluctuate very significantly, and ultimately absorption capacity for specimen treated with the soy methyl ester is very high compared to the other sealer, and higher than the untreated control. We analyzed this data because of this type of sealer contain sodium tartrate, which is base material for super absorption material. Probably most of you have an idea what the super SAP is. Whenever it comes in contact with water, absorb water and swell, and when it's kind of water is needed by the concrete, it gives the water back. So that's why we think that because sealer is act as a partial blocker, and this fluctuation is happening. I will be back to discuss about this fluctuation in the coming slide again. And the third objective of our research is chloride penetration or chloride performance. So we followed the methodology described by AASHTO T259. The only difference we followed here, instead of ponding our chloride solution for 91 days, we followed cycling for 13 cycling, which is equivalent for 91 days, and 4 day wetting and 3 days drying, which is kind of like we want to see what's the effect of the wetting and drying on the chloride penetration. We can see here again that all of the sealer treatment reduces the chloride penetration, and but most effectively we can see that soy methyl ester and silane very effectively reduces the chloride penetration compared to the sodium tartrate. So we can see that sodium tartrate was not that much effective compared to untreated control. And as I mentioned earlier, because if we are looking at the concrete that fluctuates from wetting and drying, we have more chloride for those concrete, they have a more fluctuation, while for concrete, we have a less fluctuation or less absorption and less drying. We have a significantly lower low chloride penetration. For now, we don't have that much enough data to support our statement. We are looking for the literature to collect the data from the literature. But if we don't get quite enough data, probably we are using the statistical method such as bootstrapping to generate more data from our existing data to reinforce our statement about the effect of the wetting and drying on the chloride penetration for future work. So we characterized our specimen using colorimetric method as well. We can see here after cutting our concrete sample with the dry thawing into two halves, we applied 0.1 molar silver nitrate. And after a while, because the silver nitrate is react with the chloride and forming silver chloride, which is the white color, we can see here that all of the control sample, there's a more chloride penetration, and sodium tartrate treatment is a little bit less. And however, we can see very little in the soy methyl ester and silane, which is this data colorimetric method is very consistent with the chloride profiling. We now probably most of you know that chloride profiling is very physical and very hard job to do, while colorimetric method is very easy. You can do it a lot of them in the same day. The second thing we looked for is a critical chloride threshold. We used the methodology described by OSICRET. Actually, I have been involved in developing this test method. This test method originally designed by Dr. Trejo and Dr. Pavan at Oregon State University, but I have been working for the last 3 years, and we in our result in a round robin test method, we showed that this test method is repeatable, which is mean we get the same result from the same laboratory, and repeatable, which is and reproducible, which is mean we get the same data from different laboratory. This test method is comes with two parts: the anode part, which is dog bone shape, and the cathode part. Usually, we cast them for 5 samples at the same time. And this test method, once after we cast them and we set up our material, and ironically, in the first initial test method, I casted them and I waited for all of my sample. They are activated in the first 3 days. And while in our research that we published in this report, we have a data usually activated earlier, 8 days and maximum to 25 days. We associated early activation because we casted our sample and we dried them for 21 days. We know this cover is around 5 millimeter, and it's because it's dried very well. As soon as we introduce it with the salt solution, because of the capillary suction, all of the salt is moved through the concrete cover and depassivated the steel. So I casted them again, and right now it's ongoing. That's why I wrote it's ongoing. For next time, we are designing. We are going to immerse them in the lime water at least for 48 hours, so as to we get the specimen get saturated again before to introduce them with into salt solution. And something, as I mentioned, after we casted them, we decided to kind of like modify a little bit, and we are going to install a resistor between the anode and cathode to monitor them and to find out is their penetration seal affect the corrosion rate as well or not. If we can prove that the sealer is affecting the corrosion rate, that will be very good achievement, because the sealer is very easy and you can apply to the concrete very easily. If based on our research, if we can get the apparent chloride diffusion, which is kind of like we can get from the chloride penetration, and from the second oxycrete, if we can get the critical chloride threshold, which is a red line, at that time we can, based on we can use fixed second law equation to predict effect of the different type of sealer on the corrosion rate, and predict the effect of this type of sealer on the surface life extension of the concrete structures. And I come to conclude that on my research regarding abrasion resistance, sodium tartrate and silane approved the surface concrete, while soy methyl ester negatively affected the concrete surface. And regarding moisture isotherm, all of the sealers reduced the absorption capacity, while in sodium tartrate significantly facilitated in the surface evaporation. And we want to tell people that desorption is an easy test and must be considered in the sealer selection. And regarding chloride penetration, we can see that soy methyl ester and silane substantially reduced chloride penetration for concrete that's subjected to the wet cycles of wetting and drying. That's all I have for now. Thank you so much for your time.